Hey guys, so happy Friday or Monday or Saturday or whenever you're watching this. Today we're going to start talking about vectors. I will eventually get out some information of the most commonly missed questions from the test. I'm not sure if we'll have time to go over that in class today. So either way, I'll get it to you guys. I know I linked it to the agenda for it has the questions and then the answers that people picked, but no explanation yet. So I'll try to get that in before class, so you have that too. But if you guys have lots of colors, like I do, Flair pens, you'll need them today. So if you have color pencils or if you just want to do it on your computer or your iPad, you can use different colors. But we're going to be talking about vectors. So I'm going to turn myself off here so we can talk about that. Okay, so today is going to be the start of 2D kinematics. So we talked about one-dimensional kinematics, which was motion in like a straight line, right? So back and forth, you're slowing down, speeding up, whatever. But it was like north to south or east to west. Two-dimensional kinematics is going to be talking about different directions that aren't in the same plane or not in the same line. They're not linear. So today we're going to start with learning how to draw vectors, and that's really all we're doing today is drawing the vectors and solving the resultant vector. It's really not super difficult, but it's a really, really important piece to some of the units we'll have down the line. So later on when we're in unit 4 and we're talking about forces, actually that might be 3. I'm not sure which unit it is in, but we'll be talking about forces and, like if you apply force in these two directions, what's your resultant force? So that's important for other things than just finding out like how far you went, what your displacement is. So today we're going to be talking about really just your overall displacement on things. But whenever we have, other topics down the road, we're going to apply the same methods. So today we're talking about drawing your vectors. For this, anytime we have vectors, we're talking about directions, okay? So we already know that like north, south, east, and west, but if you label them and put their angle associated with that on there, this is what you would get. So I don't want to move my cursor around too much because that little piece at the bottom keeps popping up. I need to figure out how to just turn that bad boy off. Okay, sorry for the pause. I tried to turn it off, but I can't figure that out. So if anybody knows how to do that, let me know. So anyway, so when you're drawing a vector, you're always going to compare it to your compass directions, right? So if you were going to get the angle of something, the angles are very important in the description of where your line should be placed. So here we have north is 0 degrees, east is 90 degrees, south is 180 degrees, and then west is 270. And then you have your directions in between those. So we have northeast is 45 degrees, southeast is 135 degrees, southwest is 225 degrees, and northwest is 315 degrees. So when you measure your angles, you measure it counterclockwise from north, okay? So if you're looking for your whole angle from north, you could say that it's 113 degrees. So if it is just a value with no direction associated with it, like if you see something, it just says 113 degrees, it's being measured from north, okay? So 113 would be down, 113 degrees away from north. Most of the time, you're going to see it represented like this one right here in the middle, where it says E 23 degrees S. What that means is that it is 23 degrees south of east, which I know is kind of a weird thing to look at here, but basically you are reading it from the middle to the right to the left. So you'll have 23 degrees south of east, and that's how you would measure this. Most of the time it'll be like this. So you would say, okay, I'm south of east, so here's east. I need to measure 23 degrees south of east, and then draw your vector line. So you'll have two things that you're paying attention to. You'll have your angle that you want the line to be at and the magnitude of that vector line. So if it needs to be 3 centimeters long, it needs to be drawn 3 centimeters long and measured 23 degrees south. You do need a protractor for this. And if you don't have a protractor at home and you can't get a hold of one, let me know. There's also just paper versions of protractors that you literally can just print it out and cut out, the center so you can use it. So you could do that. But if you don't have access to a protractor and you need one and you can't print one off, let me know and I can get one for you. It's not a huge deal. I can send it to your house or you can come pick it up from the building. Okay, sorry about that. So anyway, you might also see it written like this. This is a very obvious, right? So 23 degrees south of east, but this one in the middle here is where we will be at most of the time. So if we draw another one, another example here, you have this line. So we're on the west, vector, and it's closer to your west line here. So you could say this is 285 degrees. If you measured it from north, you went all the way around, this would be 285 degrees. Or you could say it's 15 degrees north of west. Okay, so what that means is that you're north of west, so you're gonna look at your west line, you measure 15 degrees upward towards north, and that's where that line would need to be placed. So just some more examples. You kind of get the idea, hopefully. So you're always measuring it. Normally you want to go from your closest vector direction. So I would go west of south or east of south. You could say north of east or south of east, and so on and so forth. So we'll get a lot of practice in. And hopefully you guys will pick up on that if you aren't understanding it yet. Okay, so I want you to just remember that vectors have magnitude and direction. So we just tested over that, right? So a scalar quantity would just be 3 centimeters, but a vector quantity includes the direction, and that's really important. So the direction being involved with the vectors is the reason why drawing the vectors and solving them is useful, okay? I know most of you have probably done this type of thing in math before with solving vectors algebraically, and that's useful too, and we will learn how to do that, but there's also a use for this. So there's a use for drawing them out because it's a visual representation of the movement, and it also shows it shows not only the scalar quantity, but also the direction. So you do lose the direction piece of that whenever you're talking and when you're solving it algebraically. And then you have to go back in and figure out the direction based off of the angles and stuff. So both have their uses. Sometimes people complain about drawing vectors because it takes a little bit of time, but this is the most representative of the true vector in the sense of it being a vector having magnitude and direction. So when we draw vectors, we're usually going to start out with some sort of guide, that there's the compass of north, south, east, and west. Once you figure out where your coordinates are, you're going to measure your angle. Okay, so once you measure your angle and you know where you want your line to go, you start at the center of your, let's see if I just draw one on here. So if I have my coordinate lines here and then change color, you're going to start at the center. So if I say it's 45 degrees south of east, okay, so 45 degrees south of east, I know that I want that angle to be this direction, but then I'm also going to have some kind of distance quality associated with that. So I might say that it's 2 centimeters long. So I would draw a straight line from here. That's not a straight line. Make sure you guys use rulers. But if my measurement was 45 degrees south of east, I would figure out where that angle is, and then draw a straight line at the length that it needs to be right here. The very end of that should just be at the end of the length that you measured, and then you add the arrow tip, the arrow point onto it. The arrow point should not add to the length of your line. Okay, so if you draw a line and let's do one in green. So if I draw a line and I'm like, okay, so I just measured this, don't come in here and do this. Okay, do you see what I did? So don't add the tip of the arrow like way off the edge, because that's messing up your measurements and it's not going to be to scale anymore. And you don't want that. You want everything to be to scale. Okay, so let's erase that. All this stuff. Oh, all right. Do it the long way, I guess. All right, so here's some examples where we would draw vectors. So of course you guys would have a protractor and paper to write on. I know that there's some apps that allow you to draw on a graph with a protractor, like a digital protractor. I'll have to look that up and see what that is. I know that's available. I don't know if you guys have it on your iPads or if you're allowed to download it or what that is, but I know it exists, so it might be something to look into if you find it before I get back to you about it. So anyways, if you're drawing these out on paper, some examples like A would be 25 centimeters north. That's very simple, right? So you're going to draw that line straight from the center of your coordinates north. You're going to measure it. It's going to be 2.5 centimeters north. Okay, so that's what this would be. For B, we have 1.9 centimeters southeast. So there's no angle given to this, so we're just going to assume that it falls right in between. So southeast would be right in the middle here. We need our line to start at the origin and go 1.9 centimeters in southeast direction. Okay, so this is measured. On C, you have a specific angle given. Okay, so this is 20 degrees west of north. So we are west of north. So we know we're going to be in this quadrant here. We're going to measure 20 degrees over. So 20 degrees west of north. So somewhere right in here. So you would measure that with your protractor and then draw the line 1.5 centimeters long. Okay. So this is 20 degrees west of north. So you're going to always draw your vectors from the common starting point and label them with the variable. You need to always label it with your variable. You can use different colors to differentiate between different vector lines, but you always want to, I know it's sometimes people aren't super neat with things when you're drawing, but vectors have to be neatly drawn. It's really important because you're going to be drawing them to scale and then measuring and solving the resultant vector from your drawing. So they do need to be neat. You do need to measure things like this, like keep your vectors thinly drawn. Don't have a big fat line. Because if you're measuring it in centimeters, if you have a very wide line because you used a wide marker or something, I mean, that could throw off your measurement a couple millimeters, which really could make a difference. So you don't want to do that. So make sure you're drawing it neatly, keep your lines thin, accurately drawn, and then please pay attention to your magnitude and direction. That's the most important part. So here's just more examples. So you might get questions like this. So the vector you're drawing, and this is the variable for the vector would be A, with a little hat on it because it has magnitude and direction. So 3.0 centimeters north, so we would measure that out. 3.5 centimeters east, so you have B here. C goes west, D goes south. Those are very easy. Notice how the magnitude of the line matches the magnitude of the measurement, right? So my 4 centimeter line is twice as long, or almost twice as long as my 2.5 centimeter line. Okay, so they do need to represent the scale that they're showing. So E is 20 degrees east of north. Okay, so think about where east of north would be, right? So it'd be over here in this quadrant. So we're measuring 20 degrees over, drawing our line the length of 3.7 centimeters. And then you just continue on like this, okay? So we've completed F and G. Now we're going to do H, so 5 degrees north of west. So if this is west, we're going to be 5 degrees north of it, and my line needs to be 4.2 centimeters long. Okay, so it's pretty long there. So you're just continuing to add. This is just practicing drawing those vectors. So once you're comfortable with this part and measuring your vectors and drawing them in the right angle, we're going to start adding them together. And so this is where the real useful part of vectors comes in. So once you know how to draw your lines for your vectors, we're going to start adding them up. So the starting point of your vector is called the tail, and then the end of the vector is called the head. So the tail would be, like, if I'm drawing vector A, the tail is where I started to draw, and the end is going to be the head. When you're adding vectors, they call it head to tail. Okay, so if I have to draw A and B, and it just gives you some numbers to write, like whatever this would be, 30 degrees east of north, and then they're going to give you another designation for this. You're going to have to put them together so you get some sort of shape that you can find the resultant from. So the resultant is going to be the line that connects the ends. So you would draw A, and then at the head of A, you would start the tail of B and draw B in whatever direction it's supposed to be in. Once you're done with that, you draw a line from the head of A to the tail of B and connect those for your resultant vector. Okay, so if you were adding A plus B, this is what it would look like. Okay, so these are going to be your resultant vectors. If you drew this to scale and then you measure it and figure, work it back out of your scale, you can figure out the actual magnitude of that displacement. So for right now, we're just looking at, these are all going to be lengths or distances, and we're finding the displacement of that object. Okay, so, and we talked about this already, so we're just adding all these up. So here, like on the left-hand side, you have all your vectors separately drawn. So if 3 was your first one, you would draw that. So your head is here, your tail is at the end of 3. And then let's say 6 is the next, like 6 here in the middle. This is the next vector you want to draw. So you start it at the head of 3, and then you draw it until it ends. And then you start the last one at the head of this one and draw it until it ends. And then when you're done, you connect the head to the tail. Okay, does that make sense, hopefully? So you should end up, no matter how many vector pieces you have, you're always going to have a resultant vector that connects the head where you actually started to the tail at the very end. So everything is always head to tail, head to tail. So how we are going to use this with adding our vectors using scale diagrams. So we know that we can add our vectors using scale diagrams because we talked about that just a second ago. So in order to do this, you have to figure out the scale for the space that you have in order to scale your lines appropriately so that you have accurate representations of the motions. So an effective way of determining a good scale to use is to divide your longest vector by the amount of space that you have and then round up. So if I have, let's say one of my vectors is representing 700 meters, okay, you're not going to draw a line that is 700 meters long, obviously. But if you're drawing it on your paper, you might have a space of 10 centimeters to draw that in. Okay, so if you have your longest vector is 700 meters, you would have 700 divided by the space for your graph. So I'll show you guys examples of that so that it's always to scale. So an example of this, so if you're adding these vectors, you have 453 meters, 25 degrees north of east, and then you have 577 meters, 41 degrees west of north. We're going to add these using a scale diagram. We're going to find the magnitude and direction of the resultant vector. So first thing you want to do, you want to measure the amount of space you have. Okay, so we will do that on this example. Then we're going to divide the longest vector's length by the amount of space. So on this example, my longest vector was this one. Okay, so y, the vector y is 577 meters long. We're going to, okay, sorry about that. Dr. Harold popped in and was talking to me. So, okay. So once you divide it by the length by the amount of space, you're going to round that factor up to a whole value to make sure everything fits in the space. So it's kind of the same idea as when you're drawing a graph and you have to figure out, how to scale your graph appropriately. So if you know how to do that the right way, this is the same thing. So you do want it to be accurate. You want your scale to be accurate to the space you have so that when you measure your resultant vectors, you'll have an accurate answer. So once you do that, you scale each vector down to size. So we had 577 meters. The other one was like 450 something. So we'll scale those both down to size, and then you draw it out using a ruler and a protractor. So this is much better explained, shown to you. So here, okay, so I've got 577 meters was my longest vector. My space that I'm going to draw it into, like my actual physical space on my paper, is 10 centimeters. So we'll divide that, right? So you get 57.7, and look at the units, meters per centimeter, okay? So I'm going to round this up because we don't want that as our scale. That's too hard to keep track of. So we want 60. So we'll round it up to 60. This makes sure that every measurement is going to fall well within our scale. So meters per centimeter. So what we get here basically is that 1 centimeter is equal to 60 meters. That's our scale. Okay. So 1 centimeter is 60 meters. So now you have to scale down your measurements. This is what that means. So you'll scale them down. You'll have 453 meters, and you convert that into centimeters using the scale, the conversion scale you just made. Okay, so you are creating the conversion factor, and then you have to convert your lengths into the new scale. Okay, so we had 577 divided by 10. Now we have a conversion factor of 1 centimeter equals 60 meters on your graph this time that you're drawing. So we're converting that. So I have 553 meters. You would set that equal. So 60 goes on the bottom, 1 centimeter goes on top. So you'd multiply, be 453 times 1 divided by 60. Same thing here. So when you scale down your values, you're going to end up with this particular example, that the X variable was 7.55 centimeters and your Y variable is 9.62 centimeters. So now you want to draw that out nicely. So we inserted our little coordinate plane here so that you can see that. So you would draw X first because that is the first one listed. So X was, what was that one? It must have been 25 degrees north of east. Okay, so that's what we drew here. So we knew that it was going to be 7.55 centimeters long. So this would be 7.55 centimeters long, and make sure that the angle is 25 degrees north of east, because that was what was in the original example. And then we draw Y starting from the tail of X, so it's head to tail. Okay, so we put the head here at the tail of X. I have another little coordinate plane just to measure my angles from. So for this one, we were 41 degrees west of north. So we're measuring that angle of 41 degrees west of north. And then this one needed to be 9.62 centimeters long. So once you get the angle, you just draw the line, the length that it needs to be to represent the magnitude. And then your last part of this is just to connect these to make your resultant vector. So you're still going head to tail. Okay, so head of your original line is here, tail of your ending line is here. So we're drawing it head to tail, and this is the resultant vector. So this would be X plus Y. So this line plus this line. Now you can physically measure it on the paper. You measure it with your ruler. It's 9.5 centimeters. You can measure your angle here. I think this comes out to be 3 degrees. So you're using what you have to measure these out. We're not solving them algebraically. We're just drawing them out and measuring them. So then once you get your resultant vector line here, so 9.5 centimeters, Oh shoot, this is a typo. That should say 9.5, not 10.5. I am sorry. So this would be 9.5, but for the sake of this, just for the answer, let's pretend this is 9.5. So you get your measured vector, your resultant vector that you've measured, and you need to take it back out of the scale, okay? So before, let me flip back to it here, when you converted these like this, you had your original value, and then you had 1 centimeter over 60 meters. Now you're gonna have to flip that. So you're gonna have your measured value. If you're drawing your boxes, some people are drawing the boxes for dimensional analysis. This is how I do it. That's fine if you want to do it the way the slide has it, but this is the way I would do it. So I'd have 10.5 centimeters. Centimeters goes on bottom. It's 1 equal to 60 meters, because that was the scale that we created, to get you 630 meters. So this one, obviously, this is a typo. That should say 9.5. So this wouldn't be 630 actually, but that's the idea. Okay, so you draw your vector. Let's erase this bad boy. Okay. So you draw your, measure it all out, find the scale, measure it out, find your vector, and measure the vector, take it back out of the scale so you get your true measurement, and then you figure out what the angle was. So you can either measure that, or you can use the angles that were part of your equation to solve that. So that's up to you. But for this one, if we have x plus y, that would end up being a resultant vector of 630 meters, 3 degrees east of north. Okay, so your answers will vary just a little bit based on how accurately your vectors were measured. So if you scaled them slightly wrong, or you settled on a different number for the scale, like if you went ahead and rounded your scale here to 58 instead of 60, you'll have just slightly different numbers. If you measured it just a couple of millimeters off, you'll have slightly different numbers. So if you're working on this and you're trying to compare what you got to the answer key, or if you're comparing it to a friend that's also in physics and you guys aren't exactly the same, that's okay. When we're adding vectors using scale diagrams, you're going to have some variability in there. And that's just the nature of it, and that's fine. So next class, we will talk about how to solve vectors, adding vectors algebraically. But this class, we're just going to focus on drawing them out, measuring them, seeing it on paper with the different directions that are associated with those, and then measuring out the known vectors magnitude. So you guys do have an assignment. It's just a couple of these questions. It's on Canvas. So if you guys get in there and look at that, it's 4 pages long, which please don't let that be like, oh my God, because I think 2 of the pages are just like 1 problem each. So you just have space to work in. These are going to be easier to do if you are doing them on paper, unless you're just super comfortable with your iPad. I mean, that's fine if you are. If you want to do them on your iPad, totally fine with me. But it might be easier to just draw them out on paper. So if you do them on paper, make sure that your photos that you upload of your work are clear. Make sure they're close up to the paper so that you're not taking a picture from like 3 feet away, because I can't zoom in that much to read them. Canvas doesn't only lets me zoom in like 200% or something. It's not very much. So please let me know if you guys have any questions, and I will try to get the commonly missed questions up for you from the test. And if you didn't see it yet, there was an announcement I made earlier that said that I do have the test graded. So if you took the test already, I have it graded for you, or if you took it yesterday, I should say, I have it graded for you, and it is in the grade book. So please let me know if you guys have any questions, and I will talk to you next time.